So it is extremely important that we continuously monitor our networks for different reasons. We want to detect security issues, we want to debug performance issues, detect equipment failures, as well as misconfigurations. Today, global activity traffic is growing at a rapid pace. Also, the amount of threats to our networks is rapidly growing. For example, McAfee saw a more than double increase in the number of collected ransomware samples in their software. Now, IDS could keep up with the number of more threats and the higher traffic rates in our networks. The problem is that more and more traffic today is encrypted. So, for example, Google saw at the beginning of this month in their recent report about encryption that 82% of the HTTP browser on the macOS platform was encrypted over TLS. Now, that poses a significant challenge for intrusion detection systems that rely on deep packet inspection to actually work. Now, on the other hand, this also triggered a different trend, and that is the one of the more machine learning-based approaches for intrusion detection as well as network analytics. Now, the problem with that, however, is that most systems that rely on these features generally require per packet data with individual timestamps as well as individual packet sizes. Potentially every single packet goes through your network. Now, with this challenging world, we believe that network monitoring and analytics systems going forward must match these challenges. So we were thinking about what would happen if you actually design a network monitoring and analytics system, about the ideal system. And not all of these requirements necessarily are completely possible or even required, but it's just an ideal world. So we would like to have a record for every single packet that traverses our network. We don't look at payloads, we just want a packet header. Applications such as machine learning and other more complex analytics, we'd like to have full programmability, ideally on a general purpose CPU using general purpose languages. And then third, ideally this all runs at a scale of hundreds of millions of packets per second, so meaning decentralized scales. Now, some of the existing network monitoring systems achieve some of these goals, but generally only a subset. So they make some sort of compromise to achieve the subset of these goals. So we looked at these compromises, and essentially they break down to four. We only look at a small subset of your traffic, for example, only DNS traffic, but that significantly limits the set of possible applications. Then the other one is sampling, so you use, for example, only every 10th packet or so. But the problem with that is it's extremely hard to get right, and you can easily miss them. Third, and this is the most common approach that has been done for years now. So you use aggregation, so you use protocol systems like NetFlow or SFlow to essentially get aggregate statistics, so the total number of bytes per packet of packets in your flow, or in start and end time. But for these systems, like I said before, those statistics are just not sufficient. Then a more recent trend, which is actually very interesting, is using programmable forwarding engines. So, for example, high-performance switches that are programmable using a language like P4 to perform in the data plane on the device. Now, there are two problems with that. The first one is your analytics application somehow must match this very restricted environment of the PFE with a little amount of SRAM and also the different state shows. And the other problem with that is that, as I said, the amount of SRAM in those devices is extremely limited. So if you do very complex analytics, you might easily hit the point where you can do great analytics on your device, but your device is actually not able to forward any packets anymore. When you change software that's running on these devices, you typically have to swap them with a downtime, and this downtime can, we run a couple of experiments, can easily exceed 10 seconds or so. So in summary, systems either reduce the load for the software or offload process. Both of these compromises come either with loss of information, in the case of aggregation, for example, such that we only have a total number of bytes over a duration of time, or loss of capability, which means that they either just don't scale to high traffic rates, or we can use more complex applications such as machine learning. Now, in order to get a sense for the current rates of what systems can do, in order to also understand why these compromises are made, we looked at a study from Facebook about their data center, not only traffic, but also and looked at the specifications of the Cisco Tetration network analytics platform. Now, a Facebook data center is organized in clusters, and in this case, a web cluster, for example, has 176 servers, which generate around 827 per second of flow data. Now, in order to analyze this data, and we don't know exactly what applications those are, but in order to analyze this flow level data, with Cisco Tetration V, we would require 5 servers with these, very significant, CPU, 128 CPU cores, and 2 terabytes of RAM. And this is only to get flow level monitoring. In order to get insight into every single packet with per packet data, we would literally require racks full of servers. Now, we would like to challenge this and actually see if, both in programming and also hardware advances in the network, if it actually is possible to perform network analytics on cloud scale infrastructures without doing such compromises. Now, in order to do that, we started designing. We first looked at different approaches that soon came to the stage where we started building our own prototype for such a system and actually see what the challenges when designing such a system are. So in our opinion, a full network monitoring and analytics solution would be composed of 2 parts. The first one being a lossless telemetry system that generates packet high rates and then sends those records to some processing platform where we can use a general purpose programming language to perform analytics, get statistics, generates alerts, and so on based on this data. Now, we set a couple of goals or thought about what we want to achieve. And for the telemetry part, modern switches can forward something around between 3 and 6 terabits per second of data. And this could evaluate to around 150 million packets per second, so that would be a good target number. And then at this rate, we'd like to have per packet information, so as well as TCP flags, per packet byte counts, and so on. Now, on the processing side, this would mean in order to do complex applications with this data, we would require a general purpose CPU that is programmable using normal languages, runtime, and a good target number for the software processing side would be something around 10 million packets per second, or packet records per second per core. Now, the remainder of this talk is about our 2 prototypes that we built. The first one being a lossless telemetry system, which we call Starflow, our high-performance software processing platform, which we call Jetstream. So let's get started with Starflow. There are 2 main components that I'd like to highlight in the system. The first one being the actual record format that we generate on the switches, and then how we actually generate these records on the switch. Now, the format, we want to have something where we have per packet header fields, but in a little more efficient manner than packet records. So if you just look at packet records, it is what you would get if you run TCP dump, for example. Those records are extremely verbose. There's a lot of duplicated information, obviously. Now, on the other extreme, there are flow records. And as said before, these records have the problem of highly aggregated data. So we only get, for example, a start and an end timestamp and a total byte count. Now, our compromise here is something we call grouped packet vectors, or GPVs, which is essentially a flow record of variable length feature vectors. And those feature vectors are configurable and can contain different types of information. For example, high-resolution timestamps, packet sizes, or in this example, TCP header flags. Now, these GPV efficiency was maintaining high information granularity. And in order to evaluate that, we looked at a 1-hour CAIDA internet backbone trace of packet headers in PCAP format. So without the payload, this was 72 gigabytes. It brought us to, I believe, 9.8 gigabytes, which is a factor of 7.7. And then finally, sending the data through a NetFlow record generator left us with 2.2 gigabytes of data. However, this is obviously at the cost of per packet information. How do we actually generate these records at line rate on a modern switch? So the problem here is that these GPVs obviously have variable lengths and the space is constrained. So what we did, we implemented a custom 2-level cache data structure that generates these GPV flow records. In hardware, we programmed this and validated the system on a barefoot to Fino PFE. The system consists of 2 components. The first one is a tall cache with narrow slots for many short flows, and that is actually the majority of most of the traffic traces that we have seen. Cache of extension slots for the fewer long flows, and these slots are wider and are actually allocated dynamically in the PFE upon demand. When looking at the resource usage of the system, so when allowing megabytes of the SRAM capacity of the switch for our flow generation cache, we end up with an eviction rate of around 0.1, which evaluates to something a little more than 10 packets per GPV. Looking at our we had an average traffic rate there of around 400,000 packets per second. The lighter blue area shows the minimum and maximum. And this then came down to around 40,000 GPV evictions per second. Then the second main comment here, I'd like to highlight 3 main components. First, how we achieved scalability. Then a set of specific optimizations that we used for this very unique workload of packet record analytics. And then I'm going to talk about how a programming API for such a system could look like. So we're relying on the paradigm of stream processing, which has been around for many, many years, where essentially data is streamed from a source to a destination processor through a series of operators that run in parallel. So typically, each operator runs in their own thread. Operator somehow transforms the data and then evicts a new transformed record to the subsequent processing stage. There are a couple of systems out there, so there's not necessarily the need to reinvent the wheel. There's like Flink and Spark Streaming. Most of them rely on the Java implementation. We had significant challenges with actually reading packet records at high rates into the JVM. So actually using this architecture for packet level analytics led us to stream. Each operator that does the same task is organized in what we call a stage, and within each stage the operators can scale. Now there's always one input stage where we read the packets or either packet or GPV data directly from the network interface card, and series of these intermediate processing stages, and then at the end there's typically one or more aggregation stages where then the data is being aggregated and finally sent to some backend. Now that could be a time series database, for example, to do later analytics or for auditing purposes. Now, as I said before, within these stages, the number of threads can actually scale at runtime, and then the Jetstream runtime also automatically figures out how to load balance the records onto the subsequent stage without corrupting the local state that's being kept within each. Actually, we went even a little further, so we looked at the multiprocessor systems, and so doing that, this is based on the insight that communication across processor sockets is a lot more expensive than within one processor socket. Jetstream applications are actually composed of multiple maps to one processor socket. one or multiple actually. Yeah. Then the second thing is we looked at the characteristics of our workload, which is packet records and per packet data, with a question if you can use some of these properties to actually optimize our software implementation. Main components that are unique to this workload. The first one being network attached input. So our data always comes from the network. We can always read it from a network interface card. There's no need to support complex file systems or file formats like other stream processing systems would need to. Network records are very easy to partition along some subset of the header space, so we can do something in order to parallelize the data. Depending on application, every packet with the same source IP address or with the same 5-tuple in general will always go to the same processor, for example. Then for records, they don't have to do any complex serialization or deserialization. We're working with a fixed memory layout, and the TCP flags will always be in the more or less in the same field. And then finally, aggregation. So even though we have per packet data, it's still often reliant on some aggregation, which means that the packet rate at the beginning of the processing graph is usually a lot higher, orders of magnitude in many cases, than towards the end of the processing pipeline, which is good for performance reasons, but also gives us the opportunity, since many of these aggregation applications have implementation, to specifically optimize hash tables for the different key types that we have in packet level workloads, like a IP 5-tuple. So let's look at two of these components in a little more detail. The first one is network attached input. So modern network interface cards usually have we can often do some sort of pre-sorting, so you send like certain source IP or MAC addresses always to the same queue. Then we can actually use kernel bypass and direct memory access technologies to map these queues and read out of these queues with minimal directly into such a stream pipeline that then maps to a single CPU socket or multiple. So based on using our Starflow technology in our initial experiments, we were able to generate around 131 million packet records per second, that we then send to the processing platform. Now, the second characteristic is, as I said, many small records, and that was one of the main bottlenecks that we saw in existing stream processing systems. Since typically these systems were somehow by they can send records from one of these processing stages to the next one. And this basically burns down to the implementation of the concurrent queues that are placed between the different threads. Now, there are different design choices that you can make. So, for example, you can use arrays or linked lists. Linked lists are extremely but then arrays have the problem that they need to be implemented as a ring buffer and can yield to these like blocking situations. Then lock-free design. So locks are pretty much the gold standard for process synchronization, but there are also programming techniques like memory ordering primitives in C++11, for example, allow us to write thread-safe concurrent data structures without using locks. Then wait-free design, and there's a little code example. This basically just means that you never want to have the current thread of execution. So if I want to enqueue an element into the queue that goes to the next processing stage, if the queue is full, I don't want to block on it and just wait until there's a space available. I just tell the scheduler that I'm done here for the second and give another thread a chance to execute. And then transfer the data, instead of assembling a new data record and then copying it into the queue, it is a lot more efficient to just get a pointer directly into the subsequent queue, assemble the data there, and then set a flag that the data is complete. Now, with these different optimizations, and we pretty much implemented every subset, and we were able to design a high-performance queue where we get throughput between two threads of around 15 million, I think 54-byte packet records per second between two pairs, between a pair of processors. So, writing such JetStream applications should be flexible and intuitive, and actually the stream processing paradigm helps us quite a bit with that. So when doing that, we start with a JetStream application, which initializes the set of stages, in this case a source and a sink with the initial replication factor, as well as some set of arguments. So in this case, we want to read data from this one network interface and maybe just output packet records on the standard output. We then create a type in each of the stages using one of these queues. So there's a connect call, which is typed, obviously, because the type of the ring buffer needs to be set, which then connects the two processing stages. Finally, to start the application, we just invoke the function call operator on the application object and run the application until the workload is done or forever. Writing such a processor that can then be incorporated in a processing stage is also pretty simple. It's just a subclass of a JetStream processor class. In the constructor, we define input and output. And then finally, to do the actual logic or implement the logic, we just override the function call operator on the object. And there all the magic is happening, where you get the packets from the queue from the processor before, do your logic, and then enqueue it to the next stage. And there's a set of JetStream scheduler, whether the particular stage needs to be scheduled again, or if the stage is actually done processing. Now, looking at the performance of this, and these are very initial results and simple applications, we were able to get the second process in a very simple application that just counted the number of packets per source IP address. However, for each of these packets, at each invocation, we needed a full hash table lookup. Just passing data through a pipeline is a little faster. With just one core, we look at second. And in this case, pretty nicely and linearly, in this case, up to 4 parallel executors. And the reason why this is 4, and this experiment was performed on a Intel Xeon processor, which had 6 cores per CPU socket. We need 1 core for 4 cores for the intermediate stages, so that's the reason why the curve goes very flat starting at 4, because at that point inter-socket communication would be required. Now, putting these numbers into perspective, we looked again at this study from Facebook about their data center architecture and also traffic numbers. So one of these web clusters sends around 91 million packets per second out to either the internet or some other part of the data center. Based on this number of 2.9 million packets, 32 cores to get full packet level insight into one of these clusters consisting of 4 racks, or 64 cores for the 8 rack version. And this is 172 servers, I believe. Now, a different system that was presented at ATC application, they needed a lot more processing power. In fact, for the same workload, they would have needed 5,096 cores, or 163x overhead. Now, when you put this 32 number in perspective, you can easily buy a server with 32 cores, right? So just a little more than half the computing power of the entire cluster in this case to get packet level insight into every single packet. In conclusion, we do believe that packet level analytics at high rates are definitely within reach, even if we're not there yet. Flow system, hardware accelerated network telemetry system, and JetStream, a high performance software network analytics platform. Now, more details you'll be able to see in about 2 or 3 weeks. There will be 2 papers out there that will be published at Houston in Boston mid of July. Please come talk to us. We are definitely looking for input and opinions from the industry and collaborations. And with that, I'm happy to take any questions. Thank you very much.
I insist. You go ahead.
Oliver, great talk on this. So you're talking about you're implementing this on the Tofino chipset, you said, for the analytics capture side of it and then sending it off to your x86.
Right.
I know one of the big challenges with the Tofino chipset is packing everything in P4 along with all the other functions you want it to do. Did this actually function as an actual packet forwarding useful switch, or was the P4 program you were running pretty much dedicated to, I'm capturing packets, but helping it actually lose to P4?
Well, in this case, so the packet record generation, where I mentioned the number of 131, we were still able to do basic layer 2 forwarding at full line capacity on the other ports. Now, this other statistic is also so, as you probably know. So this is obviously then unrealistic. I mean, there is more hardware coming out with more SRAM, but I mean, the system still works, it just leads to a higher eviction rate.
Okay, so this is kind of your optimum, using the maximum resources of the chip for this. This is what you can achieve, but
yes.
Real world, okay, got it. Thank you.
Exactly, absolutely.
Hi, Avi Friedman with Kentic. Pretty cool stuff. And have some questions just to understand. So you're basically using P4, generating what's essentially vectors that go with a common stuff. And there's vectors of the arrival time, that's one vector, and then packet size and like that. Mm-hmm. Yeah, and it'll be interesting to see, how much of that gets deployed on the common switches. But you point out tetration, and I actually compete with tetration, so I have no particular feeling for them. But the Nexus 90 switch that does a flow cache primary, and then only go to tetration, which doesn't understand about internet and other stuff. So
right. I mean, I'm not saying that there's absolutely no technology. Yeah. It's pretty hard to get a sense for what is out there, especially being academia. Yeah.
But interesting question: have you thought about looking at if it's TCP sequence numbers, looking at retransmit, looking at that particular is it actually gives you a histogram of packet sizes, I think arrival times, some of the performance type stuff that switches have just been unable to give us. And just doing sampling, as you point out, to a lightweight Intel on the switch itself is not going to get that.
Right. So I mean, since we're getting histograms, for example, of the packet sizes, is also possible with this platform, mm-hmm. right? I mean, you can do certain things on the switch directly. But then this also leads to the problem of the previous question, right. where eventually there's just no SRAM available to do all of that. I mean, once we have the packet records, we can do very detailed on jitter, for example, on any latency issues, because the Tofino, for example, exports a microsecond mm-hmm. resolution timestamps. Yeah.
Or you could extend GGV to have sequence numbers or something, do more parsing. And yeah, P4. Well, I'll ping you by email. I think it's an